Okay, we will prove center manifold theorem. We proved last time. We didn't finish completely, so we will prove at least the first three. Okay. Let's start from equation. Equation of the dynamical system is given by linearized part j times x plus the remainder r of x. And here we used appropriate cutoff to cut off this remainder term r. So r has of course r is the it's a vector, and each component of the vector. So we will show the supremum norm of r is so given by supremum of r is small and bounded, and we further assume that the supremum norm of the second derivative is also bounded, is small, which means that we are assuming r to be C2 function at least. We can also write this differential equation in terms of integral equation as follows, where the t naught can be arbitrary choice. Now, using the projection operator onto the center linear space and the stable linear space and the unstable linear space, so I will apply this identity operator on both sides of the above equation. Then the right hand side can be written in three terms, as each projections applied to the right hand side of the above equation. And since t naught is our choice, we can choose our t naught differently for each term. So instead of using the same t naught, we will use different t naught for each case. So here we call tu, and for the stable manifold ts, and for the center linear space we will use 0. We define the positive number beta to be the spectral gap from the eigenvalue of the smallest positive eigenvalue of j, or the absolute value of the smallest positive, smallest absolute value of the eigenvalue other than 0. The smallest, so the smallest smallest non-zero absolute value of the real part of the eigenvalue. Choose any number, any positive number less than beta to be eta, and we assume that there's a solution that grows less than exponent eta. So for some constant c, x of t is grow exponentially but less than the exponent eta. And let's call x, the capital X eta, to be the set of such function that grows less than e to the eta t. So we can define actually the eta norm, which is just the supremum norm of x times e to the minus eta t. So of course the above function satisfies the supreme norm being finite. So consider the solution exists within this space of function. Oh, by the way, I didn't color the t naught also here, so this t naught has to be 0, this t naught has to be ts, this has to be tu, this is ts, this is tu. Let's take the first term in the stable component and estimate it for when Ts is going to negative infinity. So we are estimating this for some finite t, and Ts is going to negative infinity, which means t minus Ts will be a large number. Since e to the j will have in the stable projection, j will have eigenvalues less than minus beta or even less. So e to the j part will decay, and the smallest possible decay is e to the minus beta decay. And when Ts is going to negative infinity, the absolute value in the e to the eta Ts can be changed into minus e to the Ts, and therefore if you look at this Ts part, then you can see that it's exponentially decaying as Ts going to minus infinity. Let me write one more equation, just one more line, just to make it explicit. So since b minus alpha is positive number, if Ts is going to negative infinity, this will go to 0. So in the similar way, the second part, this part will also go to 0 if Tu is going to infinity. So we will set in both equation Ts is going to the limit where Ts is going to negative infinity and Tu going to positive infinity. So for those class of solution, if you assume x of t is satisfy the bounded eta norm, then it satisfies the following integral equation. Let's rewrite the first line by putting the projection on each term separately. And since this projection commute with the Jacobian matrix J, we can put the first projection pi center after e to the j term, and we can write this projection just before x of 0. Let's call it the projection of x0 on the center linear space to be xc. So the reason that we are defining this new term is because I want to define new notation which takes the function x and spits out the new function gamma of x, and it depends on xc. xc becomes the parameter of this functional gamma. So again, gamma of xc for each parameter xc. xc is what? xc is a function. xc is a point on the center linear space. Did I have the notation for center linear space? Let's see. Yes, we call it capital VC. So that's where the projection operator pi c is projecting onto. And each x eta space, of course, it has a norm, the eta norm. Well, eta norm is above here, so this is the eta norm. And in terms of that norm, this map gamma of xc is a contraction mapping, therefore it has the fixed point which becomes exactly the solutions to this equation. So we want to prove that this equation has a solution. This equation has a solution by this lemma. now we have this unique solution. We just proved that there's a solution to this equation in x eta space, and therefore we can define our center manifold as following. First, let's call x sub xc be the unique solution that we show that exists. So of course this unique solution is for each xc, because we show the uniqueness for each gamma of xc. And once that solution is found, then at 0, at time equals 0, the projection of that onto Vc is equal to xc. Why? Because of this fact. So that leads to this, and the center manifold is defined exactly by these points where xc can be any points in Vc. Okay, let's prove the lemma about the contraction mapping. We just want to estimate the difference being smaller than before applying the gamma. So we want to bound this difference by x1 minus x2, for example. But let's just use one of the term. So there's several terms, but one of the term. Let's consider the stable projection part. So the projection to the stable part is of the following form, and let's just take a bound of this term. First, the difference of Rx1 and Rx2 can be written using the supremum norm of the derivative. And the e to the j part also can be bounded when tau is less than t by e to the beta. Oh no, it's bounded by e to the minus. Here it's minus beta, because it's a stable. So it has to decay in time. So j has the negative eigenvalue less or equal to minus beta. And furthermore, x minus x2 can be written as the eta norm times something that grows in eta. If we do the tau integral using this upper bound, this red font, the writing in red becomes the upper bound, and if you do the tau integral, when small t is going to infinity in positive direction, then it's clear that it's decaying in e to the minus beta t. So after tau integral, this term star will be of the form some constant, and the eta norm of this and times e to the eta of absolute value of t. If we move this e to the eta term to the other side, and then if you take the supremum norm on the left over time, then that's exactly the eta norm of gamma x1 minus gamma x2. So we obtain some bound in eta norm after one, so bound of the difference after one application of gamma corresponding with respect to before application of gamma. And this coefficient of this bound, which is c, contains this supremum norm of the first derivative of r, and that can be as small as you want by choosing the cutoff function small as possible. So we can choose the cutoff such that this coefficient c can be smaller than 1, and that's where we can define the contraction mapping. So there exists some small cutoff so that this map becomes contraction mapping.